In 1964, Stephen H. Dole and Isaac Asimov got together and wrote a cute little book entitled, Planets for Man. Chapter 2. Human Requirements. Temperature. In itemizing the specific requirements necessary for planets to be habitable for man, the matter of temperature is a reasonable starting point. While it is true that human beings can endure brief periods of extreme heat and cold by using various kinds of protective clothing and other insulation, it is also true that there is a range of temperature that human beings prefer for their everyday existence, and that variations outside the zone of maximum comfort are of constant interest to us. We all know what the chief topic of conversation is bound to be on days that are unusually hot or unusually cold. Virtually all the world's human population lives in regions where the mean annual temperature is between 32 degrees F, 0 degrees C, and 86 degrees F, 30 degrees C. Fully 18% of the Earth's land area, including Antarctica, Greenland, the Arctic islands, etc., has a mean annual temperature of less than 32 degrees F, 0 degrees C, and is by our definition as uninhabitable as the moon, though easier to reach. In fact, 95% of the human population is crowded into the 65% of the Earth's land area that has a mean annual temperature between 40 degrees F, 4.5 degrees C, and 80 degrees F, 27 degrees C. It is of course not only the human desire for comfort that dictates such a narrow temperature range, it is also the fact that these temperatures are best tolerated by the agricultural crops and domesticated animals on which man depends for food. To be sure, some species of plants and animals can withstand more or less prolonged exposures to very high or very low temperatures, and a few species have become adapted to hot or cold environments, but most of the plants and animals important to man as sources of food and as suppliers of oxygen require temperatures between 32 degrees F, 0 degrees C, and 86 degrees F, 30 degrees C, for survival and active growth. In addition to the limitation that involves the mean annual temperature, there is also a limitation introduced by the daily temperature extremes experienced at the warmest and coldest seasons of the year. Thus, an area with an annual mean temperature of 60 degrees F, 15.5 degrees C, may experience a daily mean temperature of 80 degrees F, 27 degrees C, in midsummer, and 40 degrees F, 4.5 degrees C, in midwinter. Such a temperature range is clearly within habitable limits. It is conceivable, though, that another area may have a daily mean temperature of 140 degrees F, 60 degrees C, in midsummer, and 20 degrees F, minus 29 degrees C, in midwinter. The annual mean temperature might still be 60 degrees F, and yet the area would be uninhabitable. The average, in other words, is never safe unless we know that the balancing extremes that contribute to the average are not too extreme. On the basis of human tolerances, then, and assuming that human beings would not be comfortable having to stay indoors constantly over long periods of time in the more extreme seasons, we can fairly decide that mean daily temperatures of 104 degrees F, 40 degrees C, and 14 degrees F, minus 10 degrees C, at the hottest and coldest seasons would represent reasonable limitations. If this seems too conservative, remember that the figures are averages over the day. In the hot season, mid-afternoon temperatures might, even with our limitation, rise to a maximum of 120 degrees F, 49 degrees C, and in the cold season the temperatures at dawn might be as low as minus 5 degrees F, minus 20.5 degrees C. Exposure to temperatures of 120 degrees F, 49 degrees C, at even moderate humidities would result in the danger of induced fever, hyperthermia, in the space of an hour or so, while exposure to temperatures of minus 5 degrees F, minus 20.5 degrees C, even when people are warmly dressed, involves danger of frostbitten extremities after a couple of hours. On any given planet, the temperature range would vary from region to region, making for habitability in some places and not in others. Even the Earth itself, as we said above, has its uninhabitable regions, so that only about 80% of its land area is suitable for us. It is not likely that many planets can do much better than this, but they could easily do much worse. Naturally, if only isolated fragments of a planet's surface are habitable, it is scarcely worth man's while to try to colonize it. For us to consider a planet as habitable, it would seem right then to expect at least a reasonable fraction of its surface area, say 10%, to be habitable. To summarize the temperature requirements, then, we specify that a planet is habitable only if the mean annual temperature of at least 10% of its surface lies between 32 degrees F, 0 degrees C, and 86 degrees F, 30 degrees C, and if the highest mean daily temperature during the warmest season is not higher than 104 degrees F, 40 degrees C, while the lowest mean daily temperature of the coldest season is not lower than 14 degrees F, 10 degrees C. Light. That portion of the electromagnetic spectrum visible to the human eye which we call light is a waveform in which the length of the individual waves, wavelength, varies from 380 to 760 millimicrons. A millimicron, abbreviated mu, is a billionth of a meter or a 25 millionth of an inch. By using very intense artificial sources, one can stretch the limits of human vision somewhat more widely, from 310 to 1050 millimicrons. Lying generally within this slightly wider range of wavelengths but mainly enclosed within the narrower range, we find also the vision of other animals, the oriented movements of simple animals toward light or away from it, the bending of plants toward light, and so on. Most important, it is light in this region that stimulates photosynthesis, the chemical reactions whereby green plants convert carbon dioxide and water into carbohydrates and free oxygen, supplying the food and replenishing the atmosphere for the entire animal kingdom. It is quite likely that these same limits are applicable throughout the universe wherever man could find a comfortable place to live. We must also concern ourselves with the intensity of illumination, illuminance, required for human vision and for other phenomena vital to human life. Illuminance is commonly measured in lumens per square centimeter. Without trying to define the lumen, we can set a standard by pointing out that the maximum illuminance due to direct and scattered sunlight at the surface of the Earth is about 15 lumens per square centimeter. The range of illuminance over which human vision can operate is wide indeed. Human beings can see well enough to walk around with reasonable assurance if the illuminance is as low as 10 to the negative 9, 1 billionth, lumens per square centimeter. The absolute lower limit of naked eye detection of a ray of light shining directly into the eye out of very dark surroundings is lower still, about 10 to the negative 13, 1/10 trillionth, lumens per square centimeter. This corresponds to a star with an apparent visual magnitude of +8, although under the best typical viewing conditions it is difficult to see stars fainter than magnitude 6.5. There is an upper limit of illuminance too, of course. A man looking directly at a point source of light would find matters intolerable if the illuminance were of the order of 0.05 lumens per square centimeter or more. This corresponds to an object with an apparent visual magnitude of about -21. Thus the full moon with a magnitude of -12 is only 1/4000th as bright as this maximum and can be looked at with impunity. The sun with a magnitude of -27 is 250 times brighter than this maximum and cannot be looked at directly without damage to the eye. The upper limit can be raised if one deals with overall illuminance rather than with light entering the eye directly. Here many complicating factors must be considered, such as the reflecting power of surfaces and objects in the vicinity, the presence of shade and shadows, and so on. Even ordinary levels of illuminance due to sunlight at the Earth's surface become intolerably high when one is surrounded by material such as fresh snow that reflects most of the light diffusely. It is this that gives rise to the well-known phenomenon of snow blindness. Under the best and most moderating of conditions, however, an overall illuminance of 50 lumens per square centimeter, 3 times the illumination level of bright sunlight, may be taken as an upper limit. The limits set by the eye of 10 to the negative 13 to 50 lumens per square centimeter are extraordinarily broad, but other factors cut down the permissible range drastically. Daily illumination intensities for active growth in green plants, for instance, must fall between certain more limited extremes. If the illuminance is too low, active photosynthesis cannot proceed at a rate high enough to be useful, and if it is too high, growth is slowed down by what has been termed solarization. The limits have not been clearly established, but they may be set at approximately 0.02 and 30 lumens per square centimeter. The highest growth rates for terrestrial plants are encountered at intermediate levels of illuminance. For some common species of algae, for example, the highest growth rates were found in the approximate range of 0.3 to 3.0 lumens per square centimeter. Thus illumination requirements are set primarily by the needs of plants and not by the needs of vision. For habitability, the range of illuminance during the daylight hours of the growing season must lie between 0.02 and 30 lumens per square centimeter. Another factor of great importance to the growth of plants is the periodicity of illuminance, the length, in other words, of day and night. Especially in the temperate regions of the earth, plant growth cycles are determined by the relative or absolute lengths of days and nights as well as by temperature patterns. Fortunately, however, the matter of illuminance does not complicate the habitability picture as much as one might suppose. On a planet such as the Earth, the source of both light and heat is the sun. In general, any effect that would alter the quantity of heat emitted by the sun would also alter the quantity of light emitted by it. It follows then that if a planet has a habitable mean annual temperature as the Earth does, it also in all probability experiences Earth-like levels of illuminance. Furthermore, we shall see that if a period of rotation is too long, daily temperature extremes make the planet uninhabitable. The days grow too hot, the nights too cold. If the rotation is such that the planet meets the temperature requirements, then the periodicity of illumination will also meet the requirements for habitability. On the whole, then, we can conclude that a planet that is habitable in terms of temperature is also very likely to be habitable in terms of illuminance as well. Gravity. The gravitational intensity on the surface of the Earth imposes a pull of 1g, g is an abbreviation of gravity, on all objects including human beings upon that surface. Clearly, men can and do endure this for indefinite periods. Scientists cannot vary the gravitational field directly in the laboratory, but they can produce forces through acceleration, by means of a rapidly turning centrifuge, for example, that resemble high gravitational fields to a considerable degree. Such centrifugal forces involving a large angular velocity are not strictly comparable in all respects to those produced by a massive planet with low angular velocity, but they are as close as we can get. Experiments with human beings in large centrifuges have shown that relatively high levels of acceleration can be tolerated by some people for brief periods of time without permanent damage. For example, accelerations of the order of 5g, producing the effect of making each part of the body seem to weigh 5 times what it ordinarily does without any corresponding increase in muscular strength, can be tolerated by a seated man not protected by special gear for about 2 minutes. Exposed for longer than that, he experiences a blackout, that is, a loss of vision caused by an inadequate supply of blood at the eye level, since blood cannot be pumped upward by the heart in sufficient quantity over longer periods against its own 5 times normal weight. An acceleration of 4g can be tolerated for about 8 minutes, while 3g have been tolerated for as long as an hour by some subjects in several experimental runs. The subjects were seated and immobilized, however, they were not walking around or otherwise functioning in an everyday manner. At the conclusion of the 3g experiments, the subjects reported quite pronounced muscular fatigue. Other experiments conducted in 1947 at the Mayo Clinic give a sharper idea of the limitations imposed by increased gravitational fields. In these experiments, 5 human subjects were timed to see how rapidly they could scramble, creep or crawl across the end of the centrifuge gondola, a distance of 7.5 feet under various imposed accelerations. Ordinarily, the time required, averaged over 5 subjects, was 1.5 seconds. At 1.41 g the time required was 4.9 seconds, at 2.24 g it was 9.4 seconds, and at 3.16 g it was 15.8 seconds. The subjects were also timed to see how quickly they could put on a standard parachute at various g levels. The average times required by 3 subjects were 17 seconds under ordinary conditions, 21 seconds at 1.41 g and 41 seconds at 2.24 g. It seems fair to conclude that the work required to perform various acts becomes excessive above approximately 2g, and that life would become burdensome over extended periods at such a level of gravity. One might conclude, in fact, that few people would choose to live indefinitely on a planet where the surface gravity was greater than 1.25 or 1.50 g. It is true that many people who are 25 to 50% overweight, and who therefore experience after a fashion the equivalent of 1.25 or 1.50 g, live normal lives and manage to accomplish as much as or more than many people whose weights conform more closely to the standards for their heights and ages. On the other hand, it is also generally true that physical activity is more exhausting to people who are carrying an excessive burden of fat, and it is better on the whole from the standpoint of both health and performance that they not do so. Animal experiments have pointed to similar conclusions. Both plants and insects apparently can tolerate extremely high G levels, even up to thousands of Gs, but this is certainly not so for vertebrates. Chickens grown in centrifuges for extended periods of time were able to survive prolonged exposure to accelerations up to 4 g but lost weight unless the acceleration was less than 2.5 g. In these fields of high G, the heart rate increased and the rate of respiration decreased. The lifespan of small animals also appears to decrease at gravitational forces higher than 2 g, although some mice showed increased lifespans at levels between 1.5 and 2.0 g. There does not seem to be a corresponding lower gravitational limit on the tolerances of human beings, that is, there is no conclusive evidence that a certain minimum level of gravity is required for their normal physiological functioning. Manned orbital flights have shown that human beings will tolerate 0 g, complete weightlessness, for at least 5 days. To be sure, a planet with a low gravitational field may be non-habitable because it is incapable of retaining an atmosphere, but not necessarily because of any direct harm wrought on human beings by such a field. For habitability, then, we need only specify that a planet have a gravitational field of less than 1.5 g. Atmospheric composition and pressure. A habitable planet must of course have a breathable atmosphere, and such an atmosphere can be rather completely specified in terms of its component gases and their concentrations or partial pressures. As far as we know, the only essential ingredients of a breathable atmosphere are oxygen and minor amounts of water vapor, though a couple of other components are necessary for purposes other than human respiration. The requirement for oxygen may be judged from actual conditions on the Earth. The pressure of Earth's atmosphere at sea level, at or near which most human beings live, is equal to that of a column of mercury, chemical symbol Hg. 760 mm or 30 inches high. Normal air pressure therefore is said to be 760 mm of mercury. This quantity can also be called 1 atmosphere. Oxygen makes up 0.209 of the volume of the atmosphere, that is just about a fifth. The partial pressure of oxygen is therefore 0.209 atmosphere or 159 mm of mercury. It is necessary, however, to make a correction in this figure, because as air is inhaled it is also humidified in the nasal passages and throat, so that by the time it reaches the interior of the lungs it is normally saturated with water vapor at body temperature. This takes up some of the air volume and replaces a bit of the oxygen that would otherwise be present. The result is that the inspired partial pressure of oxygen, that entering the lungs, is lower than that in the atmosphere itself. Under normal conditions the inspired partial pressure of oxygen is 149 mm of mercury. At this inspired partial pressure men can and do live comfortably through extended lifetimes. This can also be done at lower inspired partial pressures. The lower limit of inspired oxygen partial pressure is approached by the inhabitants of a mining settlement at Aucanquilcha in the Chilean Andes, situated at an altitude of 17,500 feet above sea level. This is said to be the greatest altitude at which men are known to live permanently. It is considerably higher than the environment of the Tibetans, most of whom reside and work their land at altitudes between 12,000 and 16,000 feet. At 17,500 feet the inspired partial pressure of oxygen is about 72 mm of mercury, yet the miners of Aucanquilcha lead very strenuous lives and appear to be completely acclimated to the low level of oxygen pressure. To reach the entrance of the mines where they work they climb 1,500 feet each day to an altitude of 19,000 feet, where the inspired partial pressure of oxygen is 68 mm of mercury. And even these conditions may not represent the ultimate lower level of oxygen pressure that can be tolerated indefinitely by some men. The suggestion has been made by some mountain climbers that life can be carried on normally for indefinite periods at 23,500 feet, a height at which the inspired partial pressure is a mere 53 millimeters of mercury, a little more than one-third the value at sea level. We will split the difference, however, and set the lower limit of inspired oxygen partial pressure at 60 millimeters of mercury. The upper limit of inspired oxygen partial pressure has been found experimentally to be approximately 400 millimeters of mercury. This is equivalent to about 56% oxygen in the air at sea level pressure, nearly 3 times the normal amount. This limit is approached in the therapeutic use of oxygen in hospitals, where the accepted ceiling is lowered to 40% oxygen to be on the safe side. For our purposes, however, we will set the upper limit at 400 millimeters of mercury. To produce an inspired partial pressure of oxygen of 60 millimeters of mercury, our minimum, after dilution with water vapor in the respiratory tract, there must be an actual atmospheric partial pressure of oxygen of 107 millimeters of mercury. If the atmosphere is made up of pure oxygen only, this would represent the total barometric pressure and would be equivalent to just about 2 pounds per square inch. This is about 1/7 the actual barometric pressure of Earth's atmosphere at sea level, which is 14.7 pounds per square inch. The question then is whether, even though the oxygen supply meets the minimum requirement, man can exist at so low a total barometric pressure. Apparently he can. At barometric pressures slightly below this level, gaseous swelling of the body due to the formation of bubbles in the blood has been observed in experiments with animals and human subjects. Carbon dioxide and water vapor, both produced by living tissue in the course of its normal metabolic reactions, are believed to be the main gases involved in the swelling phenomenon. Thus the lower limit for oxygen partial pressure may also serve as a lower limit for total barometric pressure. The upper limit of oxygen partial pressure represents a total barometric pressure of slightly more than 0.5 atmosphere. However, by diluting the oxygen with inert gases that have no deleterious effect on the body, higher barometric pressures can be reached. Earth's actual atmosphere is diluted to a total pressure of 1.0 atmosphere, and there is no reason at all to think such dilutions can't reach considerably higher total barometric pressures. There are only certain other gases that may be mixed with oxygen without rendering the atmosphere unbreathable, and each has an upper limit of inspired partial pressure that should not be exceeded. Symptoms of narcosis, that is, of the kind of unconscious stupor brought on by narcotics or anesthetics, have been reported when inspired partial pressures of nitrogen, argon, krypton and xenon, all of which are chemically inert gases, exceed certain levels. The greater the atomic weight of the inert gases, the lower the level required for narcosis. Xenon, the heaviest and therefore the most narcotic of the stable inert gases, is narcotic at a pressure of 160 millimeters of mercury, 0.21 atmosphere. Xenon has in fact actually been used as an anesthetic in surgical operations. An 80 to 20 xenon oxygen mixture at 1 atmosphere will produce unconsciousness in 3 to 5 minutes. Krypton is narcotic at a pressure of 350 millimeters of mercury, 0.5 atmosphere, argon at 1220 millimeters of mercury, 1.6 atmospheres, and nitrogen at 2330 millimeters of mercury, 3 atmospheres. From these figures we can estimate the limiting concentration for the still lighter inert gases neon and helium, values that have not been determined experimentally. For neon it is 3900 millimeters of mercury, 5.1 atmospheres, and for helium it is 61,000 millimeters of mercury, 80 atmospheres. The actual concentration of inert gases in our atmosphere, or any atmosphere likely to be found on an Earth-like planet, is far smaller than these limits. Nitrogen, with an actual partial pressure in Earth's atmosphere of 603 millimeters of mercury, 0.78 atmosphere, comes closest. Its concentration need merely be quadrupled to reach the narcotic level. Argon, with a pressure of 6.8 millimeters of mercury, 0.09 atmosphere, is next highest, and its concentration must be increased nearly 200-fold to reach narcotic levels. Carbon dioxide, although a reasonably inert gas, takes part in certain chemical reactions in living tissue and produces narcosis at considerably lower levels than the inert gases listed above. The upper limit for the carbon dioxide concentration in a breathable atmosphere is 7 millimeters of mercury. The actual partial pressure in the Earth's atmosphere is 0.23 millimeters of mercury, but it is quite possible to find atmospheres with impossibly high concentrations of carbon dioxide. The atmosphere of Venus is very likely a case in point. Hydrogen is a special case in that while not poisonous, it is highly inflammable. Only non-combustible mixtures of hydrogen and oxygen could be regarded as acceptable. To be sure, one would never expect to find both free hydrogen and free oxygen simultaneously present in a planetary atmosphere. The first lightning stroke would end such an atmosphere even if it could have been formed in the first place. Methane, a compound of carbon and hydrogen, is similar to hydrogen in being relatively non-toxic but inflammable. Both hydrogen and methane occur in the Earth's atmosphere only in traces. They are continually being formed by the decomposition of organic material on Earth and are continually being consumed through slow reaction with oxygen. Our atmosphere contains traces of chemically active gases other than oxygen itself. These can take part in chemical reactions within the body, inactivating enzymes and distorting the normal path of metabolism. In even low concentrations, then, they are poisonous. Upper limits on the tolerable concentration of such gases as ammonia and carbon monoxide, for instance, are 100 parts per million, 25 parts per million for nitrogen dioxide, 20 parts per million for hydrogen sulfide, 5 parts per million for sulfur dioxide or hydrogen chloride, and 0.5 parts per million for ozone. These gases occur in our atmosphere in traces that are normally considerably smaller than the upper limits of concentration just listed. All such active gases, by the very fact that they are active, would be expected to react with the free oxygen and water vapor of an atmosphere such as ours and would be reduced to traces quickly, as they are in our atmosphere, even if present originally in larger quantities. There remains one common gas to be found in planetary atmospheres, and that is water vapor. Water is a special case in many ways. For one thing, it is the only common material with a freezing point within the habitable range of temperature and pressure, so it is the only component of the atmosphere that exists on Earth in the liquid and solid forms as well as in the gaseous form. Because of its special characteristics, it requires treatment in a separate section. None of the above gases other than oxygen and water vapor is known to be necessary to make up a breathable atmosphere for human beings or indeed for any form of animal life. Oxygen is directly necessary, water vapor indirectly so, to prevent dehydration of the respiratory system. The other gases, for all we know, can be completely absent. To be sure, really prolonged tests on people living in atmospheres containing no inert gases have not yet been carried out, so it cannot be stated categorically that inert gases are unnecessary. The longest test carried out on human beings in atmospheres containing no inert gases has been of 30 days duration. Some of the inert constituents of the atmosphere are vital to plant life and therefore are indirectly necessary to ourselves, even though such gases are not directly involved in respiration. The chief of these is carbon dioxide, which is the necessary source of carbon for the plant world. The normal concentration of carbon dioxide in the Earth's atmosphere is 0.03%, equivalent to a partial pressure of 0.23 millimeters of mercury. A reasonable minimal value for supporting normal plant life has not been determined, but possibly it would be of the order of 0.05 to 0.10 millimeters of mercury, about 0.01%. Some nitrogen is also needed to supply nitrogen compounds to plants and animals through indirect chemical pathways. Thus, a small fraction of the free nitrogen in the Earth's atmosphere is constantly being converted into the oxides of nitrogen by lightning flashes, and it is estimated that there are over 3 billion lightning strokes per year throughout the world. Some 100 million tons of nitrogen are converted from elemental form into compound form in this fashion, and without this conversion, plant life on the planet would not be able in the long run to obtain adequate supplies of available nitrogen to maintain itself in its present profusion. Atmospheric nitrogen is also converted to usable compounds by bacteria attached to the roots of certain leguminous plants. Decay processes are of course continually restoring molecular nitrogen to the atmosphere. The minimum necessary amount of atmospheric nitrogen to support this nitrogen cycle has not been determined, but we might place it tentatively at 10 millimeters of mercury. We are now in a position to return to the question of the maximum tolerable barometric pressure. Of all possible diluting gases, helium is safest. Helium has been added to oxygen so that the final mixture was 98% helium and 2% oxygen with a total pressure of 150 pounds per square inch, about 10 times normal barometric pressure, and such a mixture has been found tolerable for breathing purposes. Really prolonged exposures have not been studied experimentally, however, and it is not known whether much more than this can be tolerated for long times. As gas density is increased, a point is reached where there would be highly turbulent flow in the air passages of the nose and the work of breathing would become excessively exhausting. One report states that even at a pressure of 120 pounds per square inch, 8 atmospheres, the turbulence is already so great that one can actually feel eddy currents in the air as it flows through the mouth. Furthermore, only helium can safely dilute oxygen to the point where pressures in excess of 5 atmospheres can be achieved, but that much helium is extremely unlikely to occur in the atmosphere of a habitable planet because such a planet cannot retain helium. By far the most likely diluent in a habitable atmosphere is nitrogen, and nitrogen cannot build up total barometric pressures past the 3-atmosphere mark without reaching narcotic levels. A realistic estimate as to the maximum barometric pressure to be permitted in a breathable atmosphere might therefore be 50 pounds per square inch. To summarize then, the atmosphere of a habitable planet must have a barometric pressure between 2 and 50 pounds per square inch. It must contain oxygen at an inspired partial pressure between 60 and 400 millimeters of mercury, carbon dioxide at a partial pressure between 0.05 and 7.0 millimeters of mercury, nitrogen at a partial pressure between 10 and 2330 millimeters of mercury, and some water vapor. Moderate amounts of xenon, krypton and argon are permissible, and large amounts of neon and helium, though these gases are most likely to be present in traces only. Inflammable and toxic gases must not be present in more than trace amounts. Water. Water is without doubt one of the most remarkable substances in the universe, and the one most inextricably linked with Earth-type life of all kinds. For one thing, it has remarkable heat-regulating properties. Its high specific heat means that considerable heat is absorbed by water as its temperature rises, and considerable heat must be withdrawn as its temperature falls. Its high heats of fusion and vaporization exaggerate this even further as ice melts to water and water vaporizes to a gas. As a result, water is an excellent heat storer and can be used with great efficiency as an air conditioner, in the form of perspiration, for the human body, and, in the form of oceans, for the Earth itself. The oceans greatly moderate the potential extremes of the Earth's temperature range. Thus the continental climate of land far removed from the ocean is marked by hotter summers and colder winters than is the oceanic climate of islands and coastal lands at a similar latitude and altitude. In addition, water expands somewhat when cooled below 39 degrees F, 4 degrees C, rather than always contracting with falling temperature as most substances do. Its solid form, ice, is less dense than its liquid form rather than more dense, as is true for most substances. This means that water cooled to near its freezing point, 32 degrees F or 0 degrees C, rises and freezes at the surface. The ice formed remains floating on the surface, insulating the water below against further heat loss, so that even the most severe earthly winter does not freeze completely any sizable body of water. A watery environment of relatively constant temperature is thus preserved through the vicissitudes of Earth seasons, and in it life forms have originated and evolved. The incomparable powers of water as a solvent, its high dielectric constant and its high surface tension, also lend it useful properties in connection with living matter. In particular, its solvent power allows an endless number of reactions vital to life to proceed rapidly, so that life plays out its drama against water as a background. 60% of the weight of a normally lean man is water, and some forms of simple life are 99% water. It can be said categorically then that a habitable planet must have fairly large open bodies of liquid water. This is true even for land life, for not only did land life originate in the ocean, but without oceans there could be no extensive precipitation and hence no salt-free groundwater to provide the supplies of fresh water upon which all land life depends. It is very difficult to determine precisely what ratio of ocean surface area to total planetary surface area is necessary. It is clear that a certain critical total quantity of water is necessary on the surface of a planet before bodies of water can appear. If there were less than this amount, then all of the water would be in the form of water vapor or of water absorbed on the surface or between the solid particles of the rocky crust. On the other hand, a planet completely covered with water and without permanent dry land could hardly be considered habitable from man's point of view. Since we have already stated that 10% of a planet's surface must be habitable before the planet as a whole can be considered habitable, it seems reasonable to require that the ocean area be less than 90% of the total surface area of the planet. Extensive open stretches of water imply the continuing presence of water vapor in the atmosphere. This is certainly an additional factor affecting habitability. The uncomfortable effects of high levels of humidity at high temperatures are well known, but there are surely adverse physiological effects due to extremely low levels of water vapor pressure in the air too, particularly at the higher temperatures. This latter condition causes very rapid drying of the mucous membranes of the nose, mouth and throat, and continuous exposure to very low levels of water vapor pressure might well be intolerable. In a breathable atmosphere, then, water vapor pressure might vary from relatively small amounts to an estimated maximum of 25 millimeters of mercury. Other requirements. The requirements stated so far for conditions of temperature, light, gravity, atmospheric composition and pressure and water are probably the major human requisites, yet there are many others. These will be stated briefly. As we said earlier, other life forms must be present, since the very existence of free oxygen in the atmosphere depends on photosynthesis in plants. For a planet to have a breathable atmosphere, it must also therefore have the equivalent of indigenous plant life. The native plant life would not necessarily look anything like earthly green plants, nor depend on the same complicated series of organic chemical reactions involved in photosynthesis as we know it. All life on the Earth shares certain basic chemical characteristics, but life on other planets could well have somewhat different chemical substructures. For this reason, the native plants might not be edible or palatable to man, and earthly life forms would have to be introduced as sources of food for human colonists. This would probably be done in any case, since people are likely to prefer and thrive best on familiar foods. Another requirement is that there must be an absence of unfriendly intelligent beings in prior possession. Man presumably can always cope with non-intelligent life forms, however formidable. Commonly experienced wind velocities in otherwise habitable regions must be of tolerable levels. Regions in which wind velocities consistently reach strong gale force, about 50 miles per hour, or higher, would not be considered habitable. Similarly, dust normally encountered should be below certain specified levels. It has been suggested that total dust, containing less than 5% free silica, the common ingredient of sand, should not exceed 50 million particles per cubic foot of air, and that high silica dust, containing more than 50% free silica and therefore particularly damaging to the lungs, should not exceed 5 million particles per cubic foot of air. The dust level may depend strongly on the quantity of water on a planet. Water droplets forming on dust nuclei and then falling as rain represent the primary means of removing dust from the atmosphere. Thus, a planet with large oceans and high rainfall should not have a particularly dusty atmosphere, while a planet with small oceans and high winds must be a very dusty place indeed. The levels of radioactivity or ionizing radiation in the atmosphere, whether caused by radioactive materials in the crust or by high-energy particles coming through the atmosphere from outer space, must be of acceptable intensity. The average natural background radiation on the Earth's surface is about 0.003 Röntgen equivalent man, rem, per week. Somewhat more than this can be endured, and the Atomic Energy Commission specifies a steady-state tolerance level of 0.3 rem per week for workers in atomic energy plants. Such a level is too high to be applied to all men on a planet-wide basis, however, because of possible long-term genetic effects. Consequently, it would be desirable to specify dosages from natural background radiation of approximately 0.02 rem per week or less for a planet to be considered habitable. Other conditions that might render a planet non-habitable would be an excessively high meteorite infall rate, an excessive degree of volcanism, a high frequency of earthquakes, and possibly an excessive degree of electrical activity, lightning. Thus we complete a discussion of the principal requirements of human beings with respect to the environmental conditions provided by a planet. We must next move on to a consideration of the variety of planets that actually exist and to a discussion of the astronomical properties they possess. Once that is done, we will be in a position to consider how those properties fit, or do not fit, the environmental requirements of human beings.